All right, give me a moment. Okay, so let's start with number 1. Yeah, feel free to jump in at any time if you have any questions. If you want to type something into the chat box, I will try to check my chat box on a regular basis. But if I'm not checking it, or if you're not getting a response, just go ahead and speak up and let me know that you put something in the chat box. Okay, so number 1, does everybody have access to the 2012 AP exam? If not, I can always send you to the link on my website where you can print this out or you can follow along. Okay, so number 1, y equals x sine x. I think part of the issue I've saw on previous quizzes and tests is just students not recognizing the need for product rule. So to make sure that we apply product rule or recognize the need for product rule and to be able to apply it appropriately. So here, x and sine of x, these are separate expressions that are separated by multiplication. So we have to go through a product rule. We can't just do 1 times cosine x, okay? We can do that if these two terms are separated by either a plus or minus, but because they're being multiplied, we have to go through product rule. So f prime g plus f g prime. Okay, so x becomes 1, sine stays, x, and then sine becomes cosine. Okay, so derivative is sine x plus x cosine x. All right, number 2. Let f be given by the function of 300x minus x cubed. Which of the following intervals is our function increasing? So we know anything that's involving with increase and decrease, we have to rely on the first derivative. So first derivative test. So let's find our way to f prime first. Okay, so f prime, we get 300 minus 3x squared. Once we have reached f prime, we set f prime equal to 0. Factor the 3 out. Continuing to factor difference of squares, we get 10 minus x times 10 plus x. And we solve for x, we get 10 and negative 10. From there, make sure that we create our slope sine line. So critical points being negative 10 and 10. And now we choose values in each subinterval. So to the left of negative 10, I chose negative 11. Between negative 10 and 0, so between negative 10 and 10, I chose 0. And between to the right of 10, I chose 11. So we insert into the derivative function, preferably the factor form, since you don't have a calculator to plug in. It's easiest with factor form. So negative 10 in for x. 10 minus negative 11 is positive. 10 minus 11 is negative. So positive times negative is negative. So we know in this first interval, our graph is decreasing. Okay. Plug 0 in, 10 minus x, 10 minus 0, 10 plus 0. They're both positive. We know our graph is increasing. And then to the right of 10, we plug in 11. Negative times positive is negative. So our graph is relative minimum at negative 10, relative max at 10. and decreasing in these two intervals, increasing in this middle interval. So we're asking for increasing interval, so negative 10 to 10 is our answer choice. Okay, number 3, we're just going to have to recognize the need for identifying the appropriate integral rule for secant tangent. We know the derivative is secant u tangent u times u prime. So therefore, the antiderivative of secant tangent will bring us back to secant. So if we know that rule, we can identify it and simply answer that as our correct answer. Okay, number 4, f of x equals 7x minus 3 plus natural log of x. Find f prime of 1. First thing we do is we have to first get to our derivative function. So let's get to our derivative function. 7x becomes 7. 3 goes to 0. Natural log of x becomes 1 over x because natural log's derivative is u prime over u. Once we get to our derivative, we can insert 1 in for x. Or sorry, 1 in for all the x's of our derivative. So 7 and 0 doesn't get affected. But the last term, the 1 inserts for x. 7 plus 1 is 8. The slope at 1 is 8. Okay, number 5. The graph of f is shown. Which of the following statement is false? Limit as x approaches 2. So exists, that is true, because in order for a limit to exist, as long as we can pick points on either side of our target, which is 2, okay, and as long as my 2 points can arrive at the same y value, we know our graph is going to have the limit that exists. So answer choice A works. Limit as x approaches 3. We see at 3, the graph is a continuous function. So if there's a continuous function, there's no issue. Our graph is always going to, if the graph is continuous, the limit will always exist. So answer choice B is fine as well. Answer choice C, limit as x approaches 4. So here's the issue. If I pick points on either side of 4 and I try to move towards 4 along the path of the graph, I see that the graph is not moving towards the same y value, right? So if we're approaching 4 from the left side of 4, our y value is approaching 2. From the right side of 4, it's approaching 4. So the graphs are not moving towards the same destination. So that's enough for us to say that the limit does not exist. The one-side limits are not in agreement, so therefore the limit does not exist. So answer choice C is false. Okay, let's just go through each of these other options here. Limit as x approaches 5. It's continuous, so if our graph is continuous, we're never going to have any issues with limits, so our limit will also exist. And the function as x approaches, or the function is continuous at 3. That's true. We have a continuous function there. So only answer choice C is the false statement. Okay, number 6, a particle moves along the x-axis. The velocity is given by 6t minus t squared. What is the total distance traveled by the particle from 0 to 3? Now, if you had your calculator, you could just enter this in as definite integral from 0 to 3, absolute value of 6t minus t squared. But without a calculator, we would have to look at the integral on both sides and see if we can make sure that any negatives is converted to positives. So let's go through our first derivative test. Okay, so we create our velocity sign line. This is already sitting at the velocity function level. Set that equal to 0. Factor out a t. And our critical points is 0 and 3. Well, the nice thing is that between 0 and 3, there's no change in direction. So as soon as we find the integral from 0 to 3, that is going to be the distance traveled, because there's not going to be any back and forth movement or change in direction between 0 and 3. We know from 0 to 3, our object is just moving to the right. So if I plug 1 into the velocity function, I get 1 times 6 minus 1. Positive times positive is positive. So in this full interval, my graph is going to be moving to the right. So as soon as I find the depth integral of 3 of 6t minus t squared, this will give me my true distance traveled. Okay, so we go through power rule. 6t becomes 6t squared over 2. T squared becomes t cubed over 3. Substitute our upper bound minus parentheses lower bound. And we get it all the way down to 27 minus 9, which is 18. Okay, any questions so far? All right, number 7, x cubed minus 5x, x cubed minus cosine x, quantity to the 5th. Find y prime. To find y prime, we have to realize that this is a function within the function. We have to go through chain rule. So chain rule, recognize the need for parentheses to the 5th. That's the outside function. The inside function is the x cubed minus cosine x. And we take turns with each of these derivatives. So parentheses to the 5th, we go through power rule, becomes 5 parentheses to the 4th. Inside function, we create our space to the right and find its derivative. X cubed becomes 3x squared. Cosine becomes negative sign. So the two negatives become positive. And then from here, we're just trying to match with our answer choice. So choice E. Okay, number 8. Tank contains 50 liters of oil at time t equals 4 hours. Oil is being pumped into the tank at a rate of R of t, where R of t is measured in liters per hour. So R of t is a rate. Selected values of R of t are given in the table using a right-Riemann sum with 3 subintervals and data from the table. What is the appropriate approximation of the number of liters that the oil are in the tank at t equals 15 hours? Okay, so anytime I see this problem where there's an initial and displacement, I like to go through this formula where my total amount is equal to the given value plus displacement. Okay, so what did I start with, and how much progress did I make between the beginning time and ending time? So we know that if I want to find the total amount in the tank at 15 hours, I'm going to be starting at 4 because that's what's given to me. I know at 4 hours it's at 50 liters. And then I can just rely on approximation. The integral from 4 to 15 of uppercase R of t will give me the additional liters that has been accumulated, and we can add that to A of 4. So from 4 to 15, we can use Wright-Riemann sum to do the. So created all the subintervals, went ahead and I subtracted each subinterval to get the width. So Wright-Riemann sum, I'll be relying on this 353 and relying on this bottom row here. Okay, so Wright-Riemann sum, 3 times 6.2, 5 times 5.9, and 3 times 5.6. Yeah, it's a little annoying having to do this without a calculator. But hopefully we won't see too much of this on the non-calculator section where we have to do things like this, but it's going to come out to be 114.9 liters. Okay, questions so far? Okay, next page, number 9. Okay, number 9 says, let be the function defined above. For what value of k is the function continuous at x equals 2? So we know that we're dealing with continuity, and we have a piecewise function. So I think the best way to kind of step through continuity-ish or determining what issues we have with continuity with piecewise function is just to be able to step through our continuity conditions. So on the formula sheets that you guys received, let me go through the continuity conditions. First condition is, does the point exist? Okay, so the target C value is 2. So we find out, does the point exist? Second, we see, does the limit exist? Here, notice that this x doesn't equal to 2 means that this is really where the connected part of graph is, okay? The graph is here. And this is just a random point. So we really don't have to worry about one-sided limit because the graph is the same on either side. So it's not like we have two separate graphs defined on either side of 2. We can just rely on just seeing if the limit exists for that top graph. And the third condition is, does the limit agree with the order pair? So we'll get a number from the first condition, we'll get a number result from the second condition, and the third condition, we're just checking to see, are the first and second one in agreement? Are they arriving at the same? If they are, then we can say that all 3 conditions pass, and the limit must, or the function must be continuous through that point. But it's saying, for what value of k is the function continuous? So we're trying to figure out what can we define for k that will allow this to connect through that hole, if there is a hole. So first things first, we go through our seeing if the point exists. So the point is defined at 2 for k. So plug 2 in for k, we get f of 2 equals k. That's as far as we can go. Second condition, does the limit exist? Limit existing is only going to be involved with the connected parts of graph. So we're just looking at this graph portion. Remember, limit is not going to do anything with holes or within a single point. We want to know where the connected parts of the graph is. So we simply take the limit of the numerator of the top expression as x approaches 2. And if you think about limit steps, the first thing we do is we just go ahead and we plug in. Okay? We go ahead and plug in 2, and we get 4 plus 1 times 2 minus 2, which is 0. So anything times 0 is 0. Insert 2 in for x, we also get 0. So we get 0 over 0, which is indeterminate form. We are able to reduce. Once we reduce, we reevaluate, and we get 2 times 2 plus 1, or 2 times 2 is 4. 4 plus 1 is 5. So our limit is 5. So in order for the third condition to pass, we need the first two to be in agreement. So if we want to guarantee that this function is continuous, we can say k is equal to 5, because if k is equal to 5, then f of 2 is going to be equal to the limit as x approaches 2. Okay, number 10, maybe I can work this out from scratch. What is the area of the region in the first quadrant? So area is either top minus bottom or right minus left. Bounded by the graph x over 2. So y equals e to the x over 2 is similar to e to the x. So it's maybe stretched or compressed a little differently, but the shape is going to remain the same. Okay, so we kind of have an idea of what the graph looks like. Okay, first quadrant. There's my e to the x over 2, and the line x equals 2. And the x-axis, so there's my shaded region. So the area, I can just do top minus bottom. Okay, from 0 to 2. Okay, we can ignore the 0 and really just focus on the u substitution that's going to come out of this. Okay, so u substitution, we let the u value be the x over 2, and we let the, we're just trying to find a substitution for those two parts. And recall, the rule that we're going to try to work towards is this e to the u du rule, which is e to the u plus c. Okay, so our u value is x over 2, which is 1/2 x. Okay, we find the derivative, du dx. Solve for dx. Once I make the substitutions, x over 2 gets replaced with u, dx gets replaced with 2 du. I can pull the 2 out in front. Okay, e to the u is just going to be e to the u. All right, the antiderivative is just itself. Right. Once I have my antiderivative, bring my original variables back. 1/2 x. And now I can work in my bounds. Okay, upper bound first. Two over 2 minus. Careful, just because we see 0 doesn't mean that is always going to go to 0. In this case, a 0 is going to allow this exponent. 0 is still 1, so the 2 is still going to factor out the 2. Or actually, we don't even have to because it already matches our answer choice. Okay, number 11, let f be the function defined by y equals the square root of the absolute value of x minus 2. Okay, which of the following statements is true? So what's going to happen is we know what y equals absolute value of x minus 2 is. It's going to look something like this. Now, what the square root is going to do is going to kind of make it a little bit curved and a little bit pushed down. So now the graph will look something like this. And so we already know that even without the square root, there's going to be an issue at 2, where the graph is connected, but it's not differentiable, meaning that there's a sharp turn where the slope doesn't exist. So continuous but not differentiable at 2, that makes sense. It is not differentiable. All right, and it is continuous. The limit does equal to 0 because the graph does connect to 0 from both sides. And x equals 2 is vertical asymptote. Okay, vertical asymptote is only going to exist if it's in the denominator of the function. So there's no denominator here, so there is no vertical asymptote. Just answer choice A. Okay, number 12, using substitution, u equals square root of x. The integral from 1 to 4 of e to the root x over root x is equal to which of the following. So the idea is, if you look at each of the answer choices, everything's in terms of u. So let's do this. We're going to convert or use substitution. But we're also going to adjust the bounds to be in terms of u. So I'm looking at this and I'm thinking this is the best way to set this up is to maybe we let the u value be the square root of x, because this has the best chance of creating a derivative that can handle this root x and make it where I can get the x did not only go away, but leave the remaining expression in terms of a rule that we can identify. Okay, so here's my target. Find our derivative. Clean this up, cross multiply. I brought the x back down to the denominator and then I converted to a radical. So now I'm going to cross multiply here, solve for dx. Make my substitutions. Okay, the root x goes away, just like what we wanted to happen. But there is a leftover coefficient of 2 we got to keep track of. Now we still have to worry about the bounds. I can't just use the bounds 1 and 4 because the 1 and 4 would be conflicting with the variable that we see here. So we have to go through and convert our bounds to be in terms of u, and our conversion formula is by this u equals root x. So let me set this up here. If x is equal to 1, if our lower bound started as x equals 1, my u takes on the formula of root x, which is root 1, which is still 1, so it looks like it's not going to change. Convert the upper bound. Root 4 is 2. So we go from 1 to 2. Our bounds in terms of u is 1 to 2. And the reason why we leave it in terms of u is because if we look at our answer choices are all in terms of u. We're just trying to create a situation that will match with an answer choice that is appropriate. Answer choice C. Okay, number 13. Function f is defined by a piecewise function. 2, y equals 2 to the left of 3, and y equals x minus 1 to the right of 3. What is the value of the full region under the graph of f of x between 1 and 5? So just to kind of give you some reference, we don't have to draw it, but maybe it helps to kind of visualize what's going on here. To the left of 3, we have this graph y equals 2. But then to the right of 3, we have a graph that's x minus 1, which is something like this. Right, but it's only showing up here. So when it's asking for the definite integral from 1 to 5, it's asking us to total the region between the graph and the x-axis. So something like this. Okay. So we can think of it as adding up the areas under both graphs and then totaling them up. That's what I'm doing here. So within the two graphs, I'm going to treat the region from 1 to 3 as what's under the y equals 2 graph. And then from 3 to 5, I'm going to look at the x minus 1 graph. So I set up two separate integrals here. One will give me the area of the left region, and then one will give me the area of the right region. So integral of 1 to 3 of 2 dx, I go through power rule, get 2x, evaluate my upper and lower bound, I get 4. Repeat the same process for my second definite integral. We go through power rule, plug in the upper and lower bound, and we get 6. And then the area under the first graph is 4. The area under the second graph is 6. 4 plus 6 equals 10. Right, number 14. F of x is defined as the square root of x squared minus 4. G of x is 3x minus 2. Find the derivative of f of g of x. So let's build f of g of x first. So f of g of x means I'm going to take all of g of x and I'm going to insert my expression into the x of my f of x. So imagine taking your f of x and replacing that x with that 3x minus 2. And so this is what your graph looks like, or this is what your function looks like. So now it's asking you to find the derivative of this composite function. Okay, I can either just decide to FOIL this out, or I can think of it as chain rule. My outside function is the parentheses to the 1/2. My inside function is the 3x squared minus 4 squared minus 4. So if I want to find the full derivative, my outside derivative, I go through chain rule. Outside derivative is 1/2 bracket to the negative 1/2. Inside function's derivative is the 3x squared minus 4 squared. There's another chain rule here. If I do 2 parentheses to the first times the inside function derivative, so there's another chain rule going on here. Let me show that step. Sorry, the outside is just the parentheses squared. So we go through a derivative here, 2 parentheses to the first power, which is the 3x squared minus 4, multiplied by the inside function derivative, which is 6x. And looks a little messy here, trying to evaluate it at 3, but now we can insert 3 in for all the x's. And then now we're just trying to get it down to a number that matches our answer choice. Okay, so here I get 9 times 3 is 27. Let me see. X squared. Yeah, reduce to be 5 root 21 in the denominator, and then multiply this out, and it ends up giving us a reduced expression of 7 over root 5. Yeah, it's a little messy. Surprised to see this type of problem on a non-calculated question. The effort required to get it down to this answer choices is a little much. Okay, 15. The graph of a differentiable function is shown. If h of x equals the integral from 0 to x of f of t, which the following is true, we know we have to evaluate and compare h of 6, h prime of 6, and h double prime of 6. Before we find all this, let's go ahead and find all the functions that we're going to be involved with. So first I have h of x, which is here. Next up, I want to find h prime. So to find h prime, that means I need to find the derivative of this expression. And if you remember second theorem says if I want to find the derivative of a definite integral, I can just insert the upper bound into the variable. So h prime is simply just f of x. And if I want to find h double prime, I'm just making this go one derivative down, and same thing here, f of x, one derivative down becomes f prime. So let's test each of these values here. So the integral from 0 to 6 is going to be a negative value, right? So maybe something like, I don't know, it's just approximation, maybe like 18-ish, negative 18-ish. So definitely less than 0. F of 6 is directly on the graph, right? So on the x-axis. So h prime of 6 equals f of 6. F of 6 is 0. And then h double prime is f prime of 6. F prime of 6 is the slope of the graph of 6. And we see the graph is positive, the slope is positive. So to order these in ascending order, we know the negative is going to be the first, followed by the 0, followed by the positive number. So h of 6 is smallest, h prime is next, and h double prime is largest. Okay, number 6. A particle moves along the x-axis with this position at time t given by x, where a and b are constants and a does not equal to b, for which of the following values of t is a particle at rest. So let's go through and find the derivative first, because a particle at rest, it means that is where velocity is 0. So we have to find our way to velocity function first. So first things first, I'm going to get it down to the point where I can find the derivative. It feels easier to deal with it without a bunch of parentheses in the way. So I'm going to expand everything out. Remember, treat a and b like you would like a 3 or 5 or 6. Those are just constant values, unknown though. So I'm going to expand t minus a times t minus b. I get t squared minus at minus bt plus ab. Let's go ahead and find this derivative, because that will take me to velocity, and like I said, velocity to 0, and then go from there. So we find each term's derivative. T squared becomes 2t. AT becomes A, BT becomes B. AB, they're both constants, so that's going to are constants. They will give me, multiplying together, they'll give me a number, and number's derivative is 0. Okay, so we have our velocity function. We set our velocity function equal to 0. So I'm just trying to solve for t. I know it seems strange. You know, it's like, how do I know what a and b are? So right now it's not so important. Let's just solve for t. We want to figure out what is the t value that will cause my velocity to be 0. So just add a and b to both sides, divide by 2, and t is equal to 1/2 a plus b, or a plus b divided by 2. Okay, the figure shows the graph of f. F of x is the definite integral from 2 to x of g of t, which of the following could be the graph of y equals g of x. So we know that g of x must be sitting at the derivative level of f. So imagine that means we're talking about what could be the derivative graph of this. So if you look at this, this is definitely a positive slope. Maybe this is y equals mx plus b. Maybe maybe the m is 1 or 2, and the b value is to be -1. So it's asking what could be the derivative graph of this. Well, if I have y equals 1x plus 1x minus 1 being this, the derivative would be just 1, and so y equals 1 would just be a horizontal line, and that horizontal line would match best with answer choice A. Right. None of the other ones resembles a line except for B, but B, this is at -1, and we know that our derivative is going to be at y equals 1 or y equals 2, however way we interpret this graph to be. Okay, 18. This seems like a strange limit problem, but just keep in mind that your h is your variable. And first thing we do with any limit problem that's in function notation, we always just insert 0 in for h. We get natural log of 4 plus 0, which is 4. Natural log of 4 minus natural log of 4 is 0. 0 over 0 is indeterminate form. And we know that with indeterminate form, we can rely on L'Hopital's rules. L'Hopital's rule says take the derivative of the numerator, and then separately take the derivative of the denominator, reevaluate the expression, and see if that will take you to a real number. So we know natural log of 4 plus h. The derivative is u prime over u, so 4 plus h becomes 1 over 4 plus h. Okay. Natural log of 4 is the constant, so the constant's derivative is going to be 0. And the h is a variable. H's derivative is 1. So once we have our updated expression, we can reevaluate the limit, insert 0 in for h. We get 1/4 minus 0 over 1, which is 1/4. Okay, number 19. The function f is defined by x over x plus 2. What points on the graph of f have a property that the line tangent to f has slope of 1/2? So tangent line, we can relate that to derivative. So we want to basically know when is the derivative of this function equal to a slope of 1/2? So we can find f prime, set f prime equal to 1/2, and then solve for x. So first things first, we have to go through our derivative. Our derivative, we have to go through, in this case, quotient rule. So f prime g minus f g prime all over g squared. Okay, so x becomes 1. We keep the x plus 2 minus f, x stays as x. G prime, x plus 2 becomes 1, all over denominator squared. Okay, we do some cleanup. We're able to get it down to x plus 2 minus x over x plus 2 squared, which is reduced all the way down to 2 over x plus 2 squared. So once we have our derivative, we set that equal to 1/2. Cross product. Take the square root of both sides. Plus or minus shows up. We get -2 and +2. So x plus 2 equals 2. X plus 2 equals -2. We get 0 and -4. And we find both these order pairs. So 0 back into the original function will give us 0 over 0 plus 2, which is 0. And evaluate the function at -4. Insert -4 in. We get into the original function, that is. We get -4 over -4 plus 2. So -4 over -2, which is a +2. Right, so we have both those order pairs and looking for 0, 0, and 4, -2. Or -4, 2. Okay, number 20, let f of x equal to 2x plus 1 quantity cubed, and let g be the inverse function of f. So I like to go through this little chart to help kind of monitor my progress along this little diagram. I know that I'm looking for g prime of 1. I know that f and g are inverses of each other. So I know that my order pair for f is 0, 1, which means that my order pair for g must be 1, 0. So having everything filled out as much as I can just allows me to give me assurance that I'm on the right track. If I can find f prime of 0, then that number will lead me directly to my answer that I'm looking for. I know that there's going to be a numerical relationship between these two numbers. Okay, so let's work our way to find f prime of 0. But to find f prime of 0, we first have to find f prime of x. Chain rule, I think that's what we need here. Okay, so outside's derivative, bracket cubed becomes 3 bracket squared. Keep the inside intact. Times the inside function's derivative times 2. Evaluate the derivative at 0. Okay, 1 squared is 1. 1 times 3 is 3. 3 times 2 is 6. So the slope of my f graph at 0 is 6, which means that this inverse at 1 must be the reciprocal, so it must be 1/6. Okay, number 21. The line y equals 5 is a horizontal asymptote to the graph of which of the following functions. So horizontal asymptote, if we're looking at a function, we can compare if the degrees match between numerator and denominator. And if the coefficients between numerator and denominator is 5, then we know that's the results of our horizontal asymptote. So here, sine of 5x over 5, we can't quite build that relationship. There's not going to be 5 over 1, at least not with sine. 5x is just a diagonal line with a slope of 5. That's not it. Here, this is a horizontal asymptote. That's equal to 0. Here, my horizontal asymptote is 5 over -1 because I take the ratio of coefficients. That doesn't match 5. Highest degree is 2. And then I seek out the coefficients of the leading coefficients of those highest variables. 20 over 4 equals 5. And that matches what I'm looking for. Okay, 22. Let f be the function given by natural log of x over x. What's the absolute minimum? So let's go ahead and find our derivative. We know that relative max, relative min is to come from the derivative. It could be from the critical point. So to find f prime, I'm going to go through quotient rule. F prime g minus fg prime all over g squared. Okay. Okay, so f prime g, natural log, this is the top is the f and the bottom is the g. Okay, f prime g minus fg prime. So natural log of x becomes 1 over x. We keep the g minus natural log of x over g prime. X becomes 1. And then denominator squared. Okay, critical point comes from the numerator and denominator. Or just the numerator, actually. The denominator, we already know that there's a vertical asymptote here at x equals 0. We can ignore the denominator. So we clean up the numerator here. We get 1 minus natural log of x. We set the numerator equal to 0. 1 minus natural log of x equals 0. 1 equals natural log of x. Raise both sides with e as the base. I get x equals e. So my critical point is at e. And I just want to know, is the graph going to be a relative max or relative min at e? I can test points on either side of e. I'll test 1. Technically, I could choose a value right of e. I could choose maybe 2, or sorry, 3 or 4, but I think e squared is a little bit easier. We know this is definitely larger than e, and also when we plug in, we're going to be able to use log properties and inverse properties to help us get down to a number without the use of a calculator. So if I insert 1 into the derivative, I get 1 minus natural log of 1, which is 1 minus 0 over 1, which is positive. If I insert e squared in for x, 1 minus natural log of e squared, natural log of e squared, I can pull the 2 down. We get 2 natural log of e, which is just 2. And that just leaves me with 1 minus 2 over e squared. So 1 minus 2 is negative. Negative or positive is negative. So I know my graph is decreasing. So increasing up to e, decreasing after it. We know there must be a relative max at e. but it's asking for the max value. So that means finding the x value is not enough. We have to go through one additional step. We have to insert this e back into the original function and get the y value. It's asking for the y value for our answer. So e back into the original function to get our y value. Natural log of e over e over e. Natural log of e is 1 over e. That's the y value they're looking for. That's the maximum y value on this graph. Hey, 23. P of t is the size of a population. Which of the following differential equation describes the linear growth and the size of the population? So differential equation is just basically a derivative, and we want a derivative that's linear. So that's basically saying when is the graph going to be linear? Linear is going to have to be a constant so that it can be a horizontal line, and this is the only horizontal line that we see without a variable. Okay, next page. Right, 24, g of x equals x squared e to the kx, where k is a constant. For what values of k does g have a critical point? So we know that critical point comes from the derivative, so we'll make our way to the derivative. Once we get to the derivative, we can insert 2/3 in for x, and we can kind of work backwards and solve for k, because critical point is where g prime is equal to 0. But we'll find g prime first. We'll get that g prime equal to 0 and kind of work backwards, see if we can solve for k. Okay, so here's my f prime g plus f g prime. X squared is my first function. E to the kx is my second function. X squared becomes 2x. We keep that e to the 2x, e to the kx plus x squared times, now the derivative for e to the kx is e to the kx times k, because the derivative for e to the u is e to the u times u prime. So the derivative of kx is just going to be k. We replace our g prime with 0, because to find a critical point, we're going to have to set our derivative equal to 0. And now we can just replace our x with 2/3 and try to find our way to our k value. Right, replacing, well, let's see, some things can also cancel out already. I can bring the first term to the left side of the equation. I can get the e to the kx completely go away. I'm just left with negative 2x equals kx squared. Continue reducing one of the x's. I'm left all the way down to negative 2 equals kx. Replace x with 2/3. Divide both sides by 2/3, which is the same thing as multiplying by the reciprocal. Negative 2 times 3/2 is negative 3. All right, solving a differential equation. We can start off by the right side over 1, so I can see that cross multiplying. I like to cross multiply in the way that will allow my dy to be on the left side, everything else on the right side. And once I have that, I'm just deciding, do I have to move anything else to get the x's on one side and the y's on the other? Okay, full separation here. So take the antiderivative, 1 becomes y, sine x becomes negative cosine. Once we have our equation, we don't forget about to include the plus c. And once we have that plus c, you can use your order pair. My order pair is pi 1, pi in for x, 1 in for y. Find your way to the c value. Once you have your c value, then you can update that c value back into where you initially made that substitution. Okay, let g be the function with first derivative by g prime, which is the following be true on the interval from 0 to 2. Okay, so the derivative is already the integral from 0 to x of e to the negative t squared. Now, e to the negative t squared is 1 over e over t squared. And that's always going to be positive, even if the graph may look something like this. All right, it's always positive, which means that if this is the derivative graph, anything that sits above the x-axis is going to represent positive slope. So anything above the x-axis is still positive. I know my slope is always going to be rising, always positive. If my g prime is always positive, that means my original graph is always going to be rising, even though it looks like here. Now the second derivative, because the first derivative will bring me down to e to the negative x squared, because I can remove that integral notation. And then the second derivative, which is e to the negative x squared's derivative, would be e to the negative x squared times negative 2x. Oh, sorry. This is the derivative here. So the second derivative will just be removing this integral notation. And we know e to the negative tx squared is a positive value. So we know that g double prime is always positive because e raised to anything, doesn't matter if it's positive, negative, or 0, it'll always be positive. So our graph, if it's second derivative, we know our original graph is going to be concave up. So concave up and increasing, answer choice A. Okay, 27. X plus y times dy dx equals 2x minus y. What's the value of the second derivative at 0.30? So that notation, that d2y or dx2 is saying second derivative. So I'm going to make my way to the second derivative. I see there's implicit going on here. And maybe it's easier to just solve for dy dx to begin with. So I'll divide that x plus y to the right side. Okay, so I'm going to go through quotient rule to make my way down another derivative. So f prime g minus f g prime. 2x minus y becomes 2 minus dy dx. We keep the denominator minus, keep the numerator, and then the denominator's derivative of x becomes 1, 2y becomes 2 dy dx, all over the denominator squared. So now that I have my second derivative, I'm going to replace every x I see with 3, every y I see with 0, and if I see any dy dx is in the way, I'm going to evaluate the 3 and 0 into the original derivative and find those values. And it looks like it ends up being 2. So I'll insert 2 in for all the dy dx's and see what that pans out to be. Okay, it's a little messy here, calculator, but we're just going to try our best to try and get it all the way down to a point where we can recognize this to be a positive or negative. So 2 minus 2 is 0. That's going to wipe all of this out. And here I get negative 6 times 5, which is negative 30. So numerator is negative, denominator is positive. So negative or positive is negative. Negative 10/3. Answer choice A. Okay, for t greater than or equal to 0, the position of the particle moving along the x-axis is given by x of t. What's the acceleration of the particle? So that means I have to move or make my way down to the second derivative, position to velocity, and from velocity to acceleration. So v of t, sine becomes cosine, cosine becomes negative sine, but the two negatives cancel out. Okay, it says, what's the acceleration when the velocity is first equal to 0? So I need to figure out the time value when velocity is equal to 0. So I do need to take a pause and actually set the velocity equal to 0 and see if I can make my way to solve for t. So 0 goes cosine plus sine. Negative sine equals cosine. Divide both sides by cosine. Tangent equals -1. So where is tangent equal to -1? It's going to be at intervals of pi over 4. But we know that tangent is going to be negative in the second and fourth quadrant. So we'll locate the second quadrant there. T is equal to, it says the first instance. So we'll choose the first value that pops up, which is 3 pi over 4. So we can set that aside and move on to the acceleration. So acceleration is the derivative 1 further down. So cosine becomes negative sine, sine becomes cosine. Replace all of our t values with 3 pi over 4. And we know that sine and cosine of 3 pi over 4 will just be variations of pi over 4 in the first quadrant. And they're both, well, 3 pi over 4 is going to be, sine of 3 pi over 4 will be positive, but cosine of 3 pi over 4, second quadrant, cosine will be negative. So root 2 over 2, we'll make our substitutions, do some cleanup, and we can get it all the way down to negative root 2. And that's our answer choice A. Okay, any questions so far? Okay, let's go to 2014 calculator portion. Okay, the graph of the function f is shown in the figure above, for which of the following value is f prime positive and increasing. So f prime positive means positive slope. F prime increasing means that my second derivative is positive, which means concave up. So this is the original graph here. The only place I see positive, any of these points where there's positive slope. So A is not positive slope, B is not positive slope, D is not positive slope. We're just down to D and E. But then what we can use to differentiate between our last two remaining answer choices is looking for concave up. C is part of a concave down graph, but E is part of a concave up graph. So answer choice E. Okay, 77. Let f be the function that is continuous on the closed interval from 2 to 4. it's nice to have this graph, have a visual perspective here. So my order pair is 210 and 420. Which of the following is guaranteed by intermediate value theorem? I may not know if the graph is continuous. The graph may kind of flip-flop. It may rise a lot higher and lower, but we know it has to cross through every single point between y equals 2 and y equals 20. So 13 falls into that range. So we can guarantee that the graph is going to hit y equals 13 at least one point in the interval from 2 to 4. F of 3 equals 15. That's not guaranteed. We just know that it's going to be between 2 and 4. It could be 2.5, it could be 2.7, could be 3.1. Okay. Maximum between 2 and 4 is possible, but we can't guarantee it. F prime of x equals 5, at least one solution on the interval. So that's going back to something like mean value theorem, but mean value theorem, my endpoints does not produce. Oh, actually, it does produce 5, but there's no statement about differentiability. So we can't do mean value theorem if there's no statements about that our graph is a smooth curve all the way through. And then part E, slope is greater than 0 for all values between 2 and 4. That's possible. That's the way I drew it. But it's also possible that our graph may dip down and come back up, or come up and go up and dip down. We can't guarantee without looking at the graph that our slope is always going to be positive in this interval. Okay, 1 second. Okay, 78, the graph of e to the tan x minus 2 crosses the x-axis at one point on the interval from 0 to 1. What is the slope of the graph at this point? So what we can do is we can sketch this e to the tan x minus 2, okay, and then look for the x-intercept. You graph the function, look for the x-intercept, and if you look at the x-intercept, it's going to cross at 0.606, and then we can set that point aside, and then we can go to our calculator, and we can evaluate the derivative at 0.606. So I don't have my graphing calculator on me right now. I'll have it tomorrow. But here, once I find that 0.606, another way you can do this, maybe it's not as efficient, but what you could also do is you can type it into your 36 Pro table edit function. And just look to see when is my graph going to cross the x-axis, meaning that when is my y value going to change from one side to the next. And if I keep adjusting my step value, I can see that around 0.605, 606 is going to be when that transition occurs. End derivative feature. I want to find the derivative of this e to the tan x minus 2. At x equals 0.606. Let's see. Okay, I need to bring that minus 2 down. So let me try that again. Okay, 2.96, pretty close, 2.961. Okay, 79, particle moves along the x-axis. The velocity is given by v of t. Acceleration is a of t. Which of the following is the average velocity? So average velocity is defined as change in position over change in time, but it could also be defined as average value theorem. So if I want to find average velocity, I'll just do 1 over b minus a, integral of velocity. So my a and b are 8 and 0 and 8. Once I put it into, adapt it for this particular problem for average value theorem, that's going to match with answer choice B. Okay, number 80, f prime is the graph that's given. Which of the following is true? So I like to label my graphs. If I'm dealing with a derivative graph, anything above is positive slope, anything below is negative slope. My critical points is the x-intercept, so -3 and 2. And I'm just looking to see where is my graph located in each of these intervals here. So to the left of -3, below the x-axis, that's negative. Between -3 and 2, positive slope. And then to the right of 2, negative slope. Okay, we can also gather information about concavity as well of the original graph. The peaks and valleys of our derivative graph is where the point of inflection is going to exist. So we know there's a point of inflection at 0, and then wherever there's a positive slope on the f prime graph, that's going to translate the concave up. Negative slope will translate the concave down. So based off of this, let's see what conclusions we can make. Relative minimum at -3, that is true. Point of inflection 2, not true. The only point of inflection we see is at 0. Concave down 0 to 4, that is true. From 0 to infinity is a concave down, and that matches with this statement. So answer choice 1 and 3. Second, guys. Okay, 81. Water is pumped into a tank at a rate of R of t, where t is number of minutes since the pump was turned on. If the tank contains 800 gallons of water, how much to the nearest gallon is in the tank after 20 minutes? So I like to use this formula. Final amount equals initial plus amount added. In this case, there's no amount that's being removed. So all we need is one moving part here. So I'll say A of 20. I want to figure out how much is in the tank 20 minutes in. I know how much is in the tank at 0 minutes. They told us is 800 gallons. And we just have to bridge the gap between 0 and 20. So the amount added from 0 to 20 of R of t. This will give me, in my calculator, will give me 420. 420 plus 800, 1220, which is I got a decimal value, but we want to round to the nearest whole number. Okay, f prime equals this graph here. So we can enter this into our calculator. After we graph it, we look for the x-intercept, and the x-intercept will tell us at 0.350. Again, sorry, I don't have my graphing calculator on me today. Okay, so this is what the f prime graph looks like if you were to put it into your calculator. So we know it's going to be an x-intercept, but how do you know which one is the local maximum? We can look to see where there it goes from positive to negative or from negative to positive. So let me label this here. We know that here at this first point, which is negative 2.314, the graph is going from a negative region to a positive region. So that's going to translate to be a relative minimum. I want a relative max. At 0.350, my graph will change from a positive to a negative slope. And then to the right of 1.234 is above the x-axis. Relative min, relative max, relative min, max 0.350. Because that's where f prime changes from a positive to a negative slope. Hey, 83. The graph gives the velocity in feet per second of a car between 0 and 8 for where t is in time in seconds of the following, which is the best estimate in the distance traveled by the car from 0 until it comes to complete stop. So we can just try to total the area under the graph here. We know this is not a geometric shape, but we'll just try our best to try to figure out maybe rectangles and triangles can help us get us there. So I see kind of a rectangle here. I drew a small rectangle, but obviously it's not going to be perfect. There's pieces that is coming out of it, or that's sticking out of the curve. And then here, this kind of resembles a triangle here. So I just did a 1/2 base times height. Either way, I'm just trying to do a very guesstimation of what the area could be. And I added up using geometric shapes. I got rectangle of 60, rectangle of 120, and the triangle of 40. I added those up. I got 220. That's the closest to 210. And so that amongst my answer choices, that's good enough for me to arrive at my correct approximation. Right, 84. Between negative 1.5 and 1.5, let f be a function with first derivative given by f prime. Which of the following are intervals on which the graph is concave down? So we basically want to graph this f prime and look to see where is our f prime graph decreasing. So wherever my f prime graph is decreasing, that is enough to show concave down. see what this graph looks like. So if I enter this in the calculator, negative 1.5. Concave down. Okay, between negative 1.5. Okay, so here's my graph. From 0 to 1. Okay. I don't have my graphing calculator on me, but if this is my f prime graph, then concave down will just be wherever my f prime is decreasing. So I'm only going from negative 1.5 to 1.5. So wherever my graph is decreasing, this interval here, and also this interval here. So from negative 1.5 to negative 1, and then from 0 to 1. Okay, more derivative graphs. Graph of f prime is shown. Where's the local maximum? So as soon as I see a derivative graph, I like to go ahead and label what I'm dealing with here. Above the x-axis is positive slope. Below the x-axis is negative slope. On the x-axis is slope 0. So my critical points, my relative max, relative min, will be at negative 3 and 1. And then label my intervals there from negative 5 to negative 3. Below the x-axis is negative slope. Between negative 3 and 1, positive slope. And to the right of 1, negative slope. Relative max must be at 1. Answer choice C. '86. F prime is greater than 0. Tells me that my entire graph has a positive slope. And we know that the integral from 4 to 7 is equal to 0, which means that the regions above and below the x-axis are going to cancel each other out. So maybe a graph that looks like this, right? Where maybe the area here is 2, and the area here, these are both areas of 2, but one is negative and the other is positive, and that ends up giving me total accumulated integral of 0. Okay, so how do we know which answer choice to choose? We can use some of these y values to help us out here. We know that our slope is positive at all for the entire graph. So from negative 4, negative 3 to 0. The issue is that this entire graph is below the x-axis. And if this is all below the x-axis, that means we're all getting negative values, and we can't guarantee that the graph is going to be below and above the x-axis to find our way back to 0. Right? We have to have an equal, potentially have an equal amount of our graph sitting below and above the x-axis. Here, let's look at answer choice C here. Negative 4 to 6 to 3. This graph is rising, but then it falls a little bit. And we know that can't be true because our slope is greater than 0 for the entire graph. So we know this is Option A is out. Option C is out. Option D, it's a slope of, or it's holding to a y value of 0 the entire time. So that means the slope can't be always rising if it's holding at a constant value. So we know that's not right. And then here, it is a positive. Getting a positive value, we're not getting enough to reduce down to 0. Okay, so if you look at part B here, -4 to 2 to 5, our y value is increasing. And we also have the possibility of the graph regions below the x-axis as well as regions above the x-axis, which gives us that possibility of creating a negative and positive region, which could cancel out to be 0. Okay, more derivative graphs here, but now we're looking at the second derivative graph. So with the second derivative graph, we have to understand that the y-axis represents not slope, not position, but concavity. So anything above the x-axis represents where the original graph is concave up. Anything below the x-axis represents concave down. Anything on the x-axis is where there's a potential point of inflection. Okay, critical points, -1, 1, and 3. Between -2 and -1, below the x-axis, concave down. Between -1 and 1, concave up, concave down, and concave up. So concave down in these two intervals from -2 to -1, and then from 1 to 3. All right, 88. This is a problem that similar triangle, rates, similar triangle problem. Very specific. We've gone through it a couple of times in class. So this is one where a person's either walking towards or away from the lamppost, and that's going to create this triangle within a triangle relationship. Let me work through this from scratch here. All right, so we know that this is going to a triangle within a triangle here. Kind of create that situation there. Person who's 6 feet tall, walking away from the base of a street light along a straight path at a rate of 4 feet per second. If the height of the street lamp is 15 feet, at what rate is the person's shadow lengthening? So I like to go ahead and label this X and Y. I'm going to create my similar triangle here. There's a triangle here in red. And there's also a triangle here I'm going to highlight in yellow. And I'll set up my proportion here. So I'll say 6, the height of the small triangle is to the height of the large triangle, as the base of the small triangle is to the base of the large triangle. Not x times y, but x plus y. So once I create that relationship here, I can cross multiply, get it down to as clean as much as I can, and then move to my derivative. Okay, so let's go ahead and find the derivatives. We can see everything that's in front of us here. Related rates, everything is in relation to time. 6x becomes 6 dx dt. 9y becomes 9 dy dt. Okay, the rate at which the person is walking, that's going to be dx dt. And then the rate at which the person's shadow is lengthening, that's dy dt. So that's the unknown. Okay, fill that in here. So 6 times 4 equals 9 times dy dt. Divide both sides by 9. And we can solve for dy dt. 24 over 9 reduces to be 2.6. And answer choice B. Okay, 89. A particle moves along a line so that the acceleration is given by a of t. If the particle's velocity is at t equals 0 is 5, what's the velocity at t equals 3? So we've been using this formula a lot with particle motion. Final position equals initial plus displacement. And we can kind of adapt it for everything with that equation, but just everything one derivative down. So instead of final position, we can say final velocity equals, instead of initial position, initial velocity, and then the displacement of velocity, which is change in velocity, which is just the integral of a of t. So everything we just move down one derivative, and we can still use this to build what we're looking for. So we're looking for v of 3, we given v of 0, and then to bridge that gap between 0 and 3, we can take the definite integral from 0 to 3 of my a of t function, my acceleration function, and I can make the calculator do the work for me here. Math 9, definite integral. I get 6.71 plus my initial velocity. So I started with this velocity, and then I increase by this velocity, and I'm left with velocity at 3 seconds is 11.710. Okay, let f be the function such that the definite integral from 6 to 20 of f of 2x dx equals 10, which of the following must be true. So notice that everything is still in terms of integral notation here. We're not really taking the antiderivative, we're just creating a different situation. But you see that what's different here is instead of 2x, it turns into just a variable t. So we have to convert that, we got to deal with that 2x somehow. So we're going to use substitution to resolve that 2x inside that f of 2x. So with u substitution, we'll let the u value be 2x. Go through our substitution steps, u sub steps. Du dx equals 2, dx equals du over 2. We make our substitution, 2 dx gets replaced with u, dx with du over 2. Okay. We pull the 1/2 out in front. Okay. But then we also need to convert our bounds to the appropriate values. So 6 and 12 are in terms of x, but notice that everything is going to be in terms of the other variable, which I can call u, which I can later turn to t. But if I want to convert the bounds so that I can match what I have here, I have to go through my conversion formula, which is this u equals 2x. So I'll take that 6 insert that 6 into the x. 2 times 6 is 12. So that's my lower bound. Upper bound was 12. Insert that 12 in for the x. 12 times 2 is 24. So I'm going from 12 to 24. But I still have that 1/2 sitting out there. So if I can somehow resolve that 1/2 over to the other side, so just multiply both sides by 2. So 2 times 10 is 20. And now if I replace the u back in terms of t, I can see that it matches best with answer choice B. All right, 91. Let f be a polynomial. Values of f prime is selected. So I find it best just to plot all these points here. So -2, 3, 0, 1, 3, 4, 5, 7, 6, 5. Which of the following must be true? Now, this is the derivative graph. So with the derivative graph, we know that the peaks and valleys of my f prime graph must be points of inflection. So I do see that there doesn't matter what else happens between these points that we don't see, but there must be at least a relative min somewhere, and there must be a relative max somewhere. And because of that, we can guarantee that there are 2 peaks and valleys. If there are 2 peaks and valleys, then the graph has at least 2 points of inflection, because peaks and valleys of the derivative graph of the f prime graph translates to points of inflection of the original graph. Okay, last one here. Cross-section problem. Let R be the region in the first quadrant bounded by the graph y equals x squared. That's this graph here. And then y equals square root of x is what's above. R is the base of a solid whose cross-section is perpendicular to the x-axis. So we have to always decide, how do we want to draw our base? And they're always going to tell you which direction to draw it in. This is x-axis is horizontal. Perpendicular, we'll make it vertical. So we want a vertical base that are squares. So let's build our base, top minus bottom, root x minus x squared. The area of a square is base squared. So insert that root x minus x squared into the slot of this formula. Root x minus x squared quantity squared. Volume formula is just the integral of my area. So I further make that substitution. And then my bound is from 0 to 1. Okay, enter this in the calculator. This is not this method. This is not washer method. So there's no pi that belongs outside as my coefficient. This is all we need. Into the calculator, we get 0.129. All right, that's all I have. Any questions? Okay, feel free to send me any reminds if you have any questions. But good luck as you continue studying, and I'll be available again tomorrow evening to go over the 2014 multiple choice, as well as any other questions that you guys may have. All right, have a great night. See you tomorrow.
All right, thank you.
See you. Bye. Thanks.
Thank you.